start recording. Okay, so I think the first thing I wanted to talk about was the assignment 7 write-up. So that was due like 5 minutes ago, and the reason I did that was just so we could actually take a look at the questions, which I have here. So let's take a look at these. First question we had was, what line of code makes the bucket class abstract? And that would have been the one line that had the virtual and the equal 0 part to it. So, oh right, this is unplugged. Wondering why this wasn't working. There we go. So now, there we go. Okay, so now I can draw. The question was, which one was the one that made the bucket class abstract? So in C++, the way you make a class abstract is not by directly marking it, which is how you do it in other languages, but you just have to have one single abstract function or more in your class, right, in order to make it abstract. So we had one there, and it was the void, and I guess it has to begin with virtual as well. Virtual void insert. How many points is the write-up? I would say, I mean, it kind of depends, but I usually try to do about 4 points per question, give or take. I guess it somewhat depends. If the questions are like very broad, then I'll do that. Kind of forgot about it. Okay, alright. I guess we can always wait the next time to do these. If you want, just try to send me an email right after class with those then really quick. Okay, maybe we'll put it off a little bit more. If anybody else forgot it too, same thing. You just email it to me. They are at the end of everything now. I know they're a new thing, so just try to remember that they're there. Because we are going to have them on the rest of the assignments. The next one coming up too. Oh, okay. I guess we'll disregard those for now, and we'll come back to it on Monday. So then maybe we'll just talk about assignment 9, and then I'm going to try to talk about more linked list stuff for as long as I can, and then we'll see how much time we have left over, and then I don't know what we're going to do after that. So here we have assignment 9, and this one's on recursion. In this assignment, you're going to have a series of these matryoshka dolls, these little, I think they're also called like nesting dolls, where you put one inside the other, right? So it's kind of recursive in that, you're using another doll to go inside of a doll itself. So we're kind of using something over and over again, which is what recursion is. So here we're going to have a series of dolls, and they're all going to have names. Let me see. I have the code here, and it doesn't have the input files, so maybe I should actually go grab those. Right, so what you're going to need to do, and I've already written main for you, so you don't really have to do the reading part, is you're going to have a list of names, and the catch here is that all the names are backwards. So we have this one, and then I have 2 other ones. So you have all these names, and they're listed backwards. So what you'll need to do is read them in order, and then we'll basically flip around the names and do a few things with the dolls. So the first thing you're going to need to do is actually work on inserting the dolls into just the other dolls, and then I believe the next part was showing that they actually were all inserted correctly by opening them, and then I think sorting them was the next part. So we'll see. We'll take a look at the actual code. So you're going to need to write a number of actual functions here, and in reality they're almost the same as the recursive linked list that we did last class. It's just the name is different, and the way we're going to think about it is maybe different, but the code itself is going to be very, very similar. So there's a few functions here. There's get name, get count, print doll, insert open, remove center, and print reverse. I think the ones that you need to implement are insert open and print reverse, but we'll see here. And then there's some other data that we keep here. So we'll keep an ID basically just to keep track of the way that we read them in originally. That way we can maybe have some sort of idea about the sorting. We're going to keep a count of the total number of dolls, which is really just used there for the sake of the ID. And then the name, which is going to be that string that we had from the file reversed. Or actually, it is just going to be the string from the file, so it is going to be this reversed one. It's going to be the backwards one. And then we're going to try to fix it and reverse it later. Let's go back to that. Right, so all the variables are there. I think the class declaration is there, and then I tried to make different colors so it's clear because I get a lot of questions. So the ones that you need to implement are these ones here in red. So I've written 3 helper functions, it looks like, for you. One is get name, which just prints the name that we get from here, so it will be one of these ones backwards. Or the way that it is in the file, which is backwards. And that will get the name. We have get count, which just returns a count. I don't think you actually need that one, but I wrote it anyways. And then we have print doll, which just prints the individual doll. So it will print the name flipped around to be the right way, and then it will print the ID so that you can actually see it. And then you will have to write, I think, 3 or 4 functions here. So there's 4 here, and then I think there's 1 in main as well. Insert, which is going to put the doll at the very center, and I'll draw an example in a moment. Open, which is going to open all of the dolls, so it's going to start with the outermost one and then work its way to the inside. And then remove center, which is going to go to the very, very center of the dolls, get that doll, and then remove it and return it. And then we have a helper function here, which you'll have to implement, called print reverse, which is going to take that name string, which is backwards, and then print it in the forwards direction by reversing the string. So that's that code that we ended up writing with the head versus tail recursion last week, is essentially the same thing here. Right, so just maybe draw a quick picture. So the insert, it doesn't seem like the pressure on this thing's working. Oh well. The insert, you're going to start with a head pointer to a doll, and it's going to be null by default. I think I may have already written that for you. Perhaps not. No, it just gives you a doll pointer. So you'll need to check it, I believe. This is really far zoomed in. Let me move this over here really quick. Where's main? Do I set the head for you? I don't remember. I might actually. I think I might have had to. Yeah, we have a pointer here called outer doll, which is basically the head pointer, which is the outermost doll in the thing. So for the first read, I should set it here. Yeah, so we'll create a doll based off the first line in the file. So I do all the file I/O for you. You just have to actually do the things that interact with it. So this one here, it will read the first doll, set that to be the outer doll, and then insert every subsequent doll. And then what you'll need to do is put that doll at the center. So what it will look like is when we do the first read, then the code that I've written apparently already puts a big doll kind of round. Yeah, it's the best doll I can draw. On the outside, right? So that's the outer one. And then whenever we insert, what you'll need to do is put a doll on the inside of that one. So it looks something like that. And then we put the next one here, and then so on. So this would be the 0th one. This would be the first one. That would be the second one. Right, so what you'll need to do is, by default, you'll notice that they have a pointer to a doll that's on the inside and it's set to null by default. What you'll need to do is follow that doll until you actually find a position where it's null and then put it on the inside. So the 0th one, that points to the first one, and the first one points to the second one. So they kind of point to the one that's on the inside here. If you notice, it's really just a linked list, but I'm drawing it in a different way. So the code might be similar. You might be able to go and take that example from last class that I wrote and kind of just modify the code. It really is the same idea. Right, so that's what the insert function does. Then we have the open function, which is going to be basically like the print function from the last one, in that it's just going to need to follow the dolls again, starting at the outmost one, and then open all the ones on the inside until you realize that there's no more dolls at the center. So once you get to 2 and you try to open it and you see that there's nothing inside of it, then you know that there's nothing more to open and you're done. So what you'll do is you'll open those, and then I believe I asked you to print it as well. And then the last function that's important for dolls is you'll need to make one that removes the center, and that one I think is the trickiest one. So that's going to need to go all the way to the center, and then it's going to need to remove it. So if I had this one here, then it's going to need to go all the way to the 2 and then take this doll out and return it. So remember that we have these pointers here. It's almost the same as a delete in a linked list, where you're just going to have to cut it out and then maybe update the pointer right above it. So if I remove 2 here, then 1 shouldn't be able to point to it anymore because it's gone. So you might, maybe as a hint, need to keep track of 2 different dolls, the one on the outside and the one on the inside, or you might want to take a look at the recursive delete that we wrote last time, which had to do a check to forward, right? It said like next. So I'll give you a hint. You might want to look 2 dolls ahead in order to be able to delete correctly. And then do an exception if the one that we're deleting is the head. We need to do something different, which actually might be handled in main for you, but that's okay. Right, so what this will do is it will remove all of the dolls from the center. So basically it's just going to put all the dolls into a vector, which is called dolls here. So you see that it pushes it back. We have it up here. So there's a vector of doll pointers called dolls. And then the last thing that it's going to do is it needs to sort them and then print the sorted list. So this part you don't really have to do anything about, but there's one more function, which is sort dolls, which is going to need to sort this vector. So you'll need to write one more function down here. And what this will do is sort the dolls based off of their names. And the problem here is that they're actually reversed. So we can't use the normal less than or greater than or whatever operator, because those aren't something that we can use when the strings are reversed. So I've written a helper function here for you called isBigger, which will tell you which of the 2 is bigger. Well, actually, it'll tell you if the first is bigger than the second, based on the reverse names instead. So I've written that for you, and this is also recursive. If you ever want to take a look at it, you'll see that isBigger calls itself, and I did that kind of just so if you wanted to look at a recursive example of like a more complicated one, then here's this. And I think this might be the most complicated recursive function in the program, but you don't actually have to write it. So and really you can just kind of be blind to the implementation and just know that it returns that if this one's bigger than the other one, then it'll return true. Right, so I think that's most of that. Let me move this back over. Right, so we went over these functions. So you'll need insert, open, remove, center, which will both delete it and then also return it. So it returns a doll pointer, being the doll from the center. We will need to do the one that prints reverse, and again, we kind of wrote that last week. And then we have these 2 other functions here, which are the global scope, which is sort dolls, which is the one you need to write, which is going to sort the dolls alphabetically. And the integer here represents the size of the list that we need to sort. So remember, we need to reduce that in some way and then have some sort of base case, and then the list itself that we're sorting. And I do recommend using that selection sort method that we talked very briefly about, where you check for the max, move it to the end, and then call the recursive case on it, which again, I think there's at least some images. I don't know if I wrote the code already for that last week. I don't recall. And then this assignment has two source files here, so you'll need to actually compile it with both of them. So you need to do both the main and the doll. Actually, I guess we should look at the file structure really quick, which is not a whole lot. But we have 3 files. This one you don't need to write anything in. This is just the header file for the doll class, and it just has all the functions declared, and that's about it. You don't need to write anything there. And then you'll need to implement them in the doll.cpp. So print doll is already written for you, and I think the reason I did that was because I was having some issues with it when I wrote the solution. So I didn't want you to have to go through that. So there's that, and then you'll just need to write sort dolls in main. So I think it's 5 functions in total, and a couple of them are really just the same, but with maybe 1 or 2 lines of code changed. As long as you have the traversal of the dolls down, as far as going from the outside one to the inside one with the recursion, which again is basically the same as a linked list if you want to look at that, then I think you'll do okay on this one. So we have a write-up, which is normal now. We have a first question, which is we explain what a base case and a reduction operator are. Won't explain that one because I think we've talked about that a fair amount. Second question, is it possible to replace any loop with recursion? And explain why we're allowed to do that, or why you can't replace a loop with recursion. And then the last one was, below is the code for factorial, which again we wrote in class, and then explain what's wrong with that function and then how do you fix it. So there's something wrong with that code, specifically maybe like 1 or 2 lines, and then what are those 2 lines that you would need, and why do we need them, for that matter. Any questions on this assignment? Probably due next Sunday, I think, but we might move it a little bit forward depending on how things go with the exam. I'm not entirely sure. Just to give you some more time to study, but I guess I'll need to double check first. Okay, don't see any questions, so I'm just gonna close that out. And then I suppose next time we'll talk about the assignment 7 write-up. Alright, so I should just close this. Okay. We'll talk a bit more about linked lists, and then we'll see where we can go from there. Because I don't want to start too much new before the final, or sorry, not the final, before the midterm review. The second midterm review. And we only really have one more topic to cover anyways, I think. So I guess I should bring that up. If I do happen to run out of time, I might put up a thread on Canvas just to ask what kind of topics you might want to talk about. Because I don't really, if we have extra classes, I don't really want to just waste them, but I might do something optional that you don't have to actually know for the final exam, but just have for the future. So I might put up a list of topics and then just let you decide what sounds the most interesting, or what you maybe want to hear about, and that could be like a number of things. So that could be, I had a list like algorithms, or it could be new data structures, or it could be parallel processing, or maybe depending on how much time we have, like application development with like GUI interface. So actually implementing graphics and not just using the command line argument. Which would be, I guess, a bit hard because we're doing C++ and I don't really know any libraries that are good for that. But maybe I can try to find something. If not, we'd have to use a different language, which I don't know if we want to do if we only have 1 class period to talk about it, or even really 2, that I think that might not be for the best. But I just wanted a heads up on that. I might post a list for that soon. I guess it kind of depends. I think we have 2 weeks following the midterm, and then the only thing I have left to talk about is stacks and queues, and I think I can probably manage to talk about them both in one day. They're really not that complicated, but who knows, maybe it'll take me 2 days. Anyways, let's talk a little bit more about linked list. Last time we talked a bit about sorting for the last maybe 10 minutes of class, and I didn't get a chance to fully explain it, but I want to come back to it in a little bit after we talk about a different kind of linked list first, and then we'll use this a linked list to maybe sort instead, or at least finish talking about the sorting, because I think it's a bit easier to do it with this type of linked list than it is with the one that we've been doing before. So with the linked lists that we've been doing, we've had this where it was a data field and then a pointer, and that was it, and it just, you know, went in a straight line until it hit null, and then it had that. I'm wondering, can I? No, I think it's still like that. Oh well. It's like not doing the pressure sensitive stuff. But I guess that's okay. Sorry about that. So right, it goes in a straight line. One pointer always points to the next one. Now one of the problems we had with this was that we couldn't go backwards, which wasn't a big deal most of the time, but it kind of mattered when we did something like deletion, I guess. And it mattered a little bit while we were doing the sorting, because when we did a deletion, right, we said if I was to delete this node and I need to remove that node from the list, then I would have to rearrange it, right? Because if I delete it, this needs to go around, this pointer needs to point all the way around there and point to the next one instead. And the way we had to do that was we had to update this field, right? So we had to update this pointer so that it points to the next thing, and then delete this. And so the problem with that, or the difficulty we had at least, was that I needed to keep some sort of pointer to the previous thing, and then I kept a pointer to the current thing, and then I would make the previous pointer point to the thing on the other side of the current, so the current's next, so that it goes to the other side of it, and then I would cut it off and delete it then, because then I know I'm not going to get any memory leaks or drop part of my list, which would also be very bad, because then I lose data that I still need. Now, a remedy for that would be if we just always kept track of a previous pointer, and so that's what we're going to do. So I'd like to introduce the idea of a doubly linked list, which is really just a linked list, but now it has a previous and a next pointer. So that's going to be part of the node itself. The node is going to have, should maybe write that in a different color so it's obvious. Let me actually write it over here. So doubly linked list, that's going to have the node class still, and then here, let's say class node, and it's still going to have the, I should have written this as a template, but it's going to have some sort of data field, and then it's going to have the node pointer, which points to the next one like we had before, and then now we're going to have a pointer to the previous one as well. And the reason we do this is just for the sake of making the deletion easier, really. There's not a huge advantage to a doubly linked list, but at least maybe will help us with some ideas down the line for some other more complicated data structures that are I think a lot more useful than linked lists. Okay, so now our structure is going to look almost the same. We're going to have a head pointer that points to the leading head of the list, and then now I'm just going to make this 3 elements long. One is going to point to the left, and then one is going to point to the right, and then here for the next element I'm going to have something similar. So this one is going to point back to the one that's pointing to it, and then have its data, and then it's going to point to the next one, which, okay, I'm running out of space here, so I'm just going to draw it downwards. And then this points up to that one, and then it has its data, and then we'll say this is the end of the list and that that's a null again. So now we have a null both at the head pointing to the left, and then a null at the end pointing to the right, and then we have the data here in the center. I'm saying center, but it's not actually an array, so it's stored with these things. Okay, so now we just have two directions, which is a little helpful, I suppose. So let's just address the three operations again that we have to do for these. Does anybody remember what the three operations that most data structures have again are? What are the three things we have to worry about? That's recording. Okay, insertion, right? That's one of them. Sorry, 1 second. I'm just trying to figure out if I can get this drawing tablet working. Oh well. Figure it out later. Okay, deletion, right? So you are both right. Those are two of them. So we have insertion, deletion, and right lookup and search. Depending on who you ask, they will use a different term. We'll just say lookup. Cool, so we'll need to do all three of those. And the only one that's going to be that much different, I think, is the deletion. Yeah, let's move a little bit over. So let's start off with that insertion. The first insertion is going to be exactly the same as it was in a singly linked list. So by default, we'll assume that the head is pointing to nothing. It's a null pointer. So it's just like that. And then when we go to insert the first thing, so now the difference here, I guess, is that we'll set the both pointers, the next pointer and the previous pointer, to null by default. So we'll set both of those to null, and then we'll worry about the addition. So when I insert the first object, I'm just going to need to make the head point to that, and then I'm done. So this is both the beginning and the end of the list, so it's okay that both the previous and the next pointer are both null. Now if I go to do the next one, then I'm going to create it, right? Was our idea is that we always create it first, and then we worry about putting it to the list. And then I initialize both of these to null, and then I need to find where to put it. And so just like before, we need to follow all of these next pointers. So I follow it until I hit the end, and then I figure out this one's the end because its next pointer is null. And then what we said before for the singly linked list was that means that I need to make it point to here. So we make this maybe a little bit lower so you can see it a little bit easier. So now I'll make it point to there. And then this was initialized to null. So what I also need to do now is make that point to the previous one. So the convenient thing about this is that we don't actually need to keep a previous as a separate variable like I did in the code before, because if you notice, when I would actually be executing the code, what would happen is we'd end up printing or pointing to this one. We always end up pointing to the last thing in the list when we do an insert, right? When we do that while loop. So what I can do here is just set this one's next equal to the one that I'm inserting, and then set the one that I'm inserting its previous equal to the one at the end, and then that's really all I have to do. So I'll maybe open up that linked list class here on the side. Right, so that's our idea there, is just we are going to set both of them. And really it's just the same after that point. Any other insert, I'm just going to need to set this previous to point back to that one, and then this one to point to the next one. Let's try to code that really quick. And then we'll try to do the deletion and the lookup. Visual Studio is just taking a little while. Alright, there we go. right. So I'm going to move this down to the corner for just a moment. Let's see. So I'm going to create a second header file and just write it all there. New item. And then we'll just call it doubly linked list. That way I can just upload this to Canvas and we'll be good. I don't know what's up with that. Alright, there we go. I'll put using namespace standard. And then now we need a new type of node. And again, I'll just make it template class. So template class T. And then we'll say node. That's it. So I need a class node. Class node. Yeah, and this should be fine. I can call it node again. No, I can't. If I include it in main, I won't. So let's just call this, I don't know, double node, so that it goes both ways. And then we'll do that. And then here we'll create a template. Class T. And then class doubly linked list. Cool. Actually, let me create this one as a struct. So we'll make this one a struct, that just so we can access all of the pointers pretty easily. So the idea here was that we had the data, which was whatever type T that we wanted to store, and then we keep two pointers, so node pointer to the next pointer in the list, and then the previous pointer in the list. And that's really the only difference that we have now. And then the doubly linked list is going to be very similar to the last one. It's going to hold a double node now of type T. We'll keep a pointer, and then that will be our head pointer. And then we'll just need some functions here. So public. And then we're just going to do those three. I think maybe we'll do a print, I don't know. So we need a void insert that takes type T, and that's the thing we're adding. I'll just call that new data again. And then we have void delete. We'll say delete at again. Int index. And then the last one we'll say lookup. And then maybe we'll change this one really quick. So let's do this to look up T search. We'll have it look up the actual data itself rather than just do an index this time, maybe to make it different and maybe a little more practical. Yeah, that's okay. We'll do that. And then I guess we'll have it return that data as well. Okay, fair enough. So let's go down here and actually write them. Actually, you know what? Let's be lazy. Let's just write it straight in the body so that I don't have to retype all this stuff. First thing we said we wanted to do was insert, and we said we wanted to, if the head was null, then we want to create the head and put that at the beginning of the list, and if not, then we needed to do that part where we set the pointers at the end. I think first things first, we should maybe make a constructor called doubly linked list. That's the default constructor, and that sets the head equal to null, and then that's all we should need. And then I suppose I'm going to need to make a constructor as well here for the doubly, or like the double node. So this one's going to have to be, it's struct, so it's public. We'll just say double node. And now this one will set, actually I guess we need a data, right? So we need t, which is the data, and then we'll set our data equal to the data we passed in, and then set next equal to null and previous equal to null. So we'll just initialize both the pointers to null by default, and then set the data to be the data that, you know, this actual node is supposed to hold. Okay. So in the insert we said we needed to account for if the head was null, then we just need to set the head equal to the new node we're creating. So let's create that node first, since we said we're going to have to do that every time anyways, so might as well. So we'll call this new node, and then this would be equal to a new double node using the data called new data that we have. Right, so if the head is null, then we want the head to be equal to the new node. Otherwise, we want to actually do the insertion part. And really, the traversal of this list, because we never have to follow a back pointer, any of these previous pointers, if we are just going to the end of the list. So the traversal of the doubly linked list is exactly the same as the traversal of the singly linked list that we did. So we'll ignore the recursive one. We'll just go up here and look at our previous insert and say, wow, okay, this is going to be exactly the same code with one extra step. So it's okay for me to just take it and basically reuse it, because they're pretty much the same idea. So here we have this. Let me tab that, or do completely delete it. That's not good. Excuse me. So the idea, right, was while we're not at the end of the list, well, the next pointer is not null, then follow the next pointer until we get to one where it is null, and then we're at the end of the list. So by the end of the for loop, our current node will become the one at the end, and we really need to do the same thing. So we need to set the next of the last node equal to the new node that we're inserting. So here, this was the last one, right? This was the current from that code. We need to set its next to point to the new node that we're creating. So maybe I should be more specific that this was the old tail, and then this is the new node that we're inserting. So we're setting the previous of the old tail, which is the node that we just found, and we are setting it equal to the new node. And then what we need to do is, because it's pointing the opposite direction, the only other thing we need to account for is that the new node, that previous pointer is going to point back to the tail, right? So the other thing I'm going to need to do is set the new node. I'm going to need to set its previous equal to, oh, and this is a type node, so I need to make this a double node. But right, we're going to need to set the previous equal to the current. So they just point to each other. We make the current node point to the new node, and the new node point to the current node, so that they both, you know, go both directions when we insert it. And then I think just for the sake of the example, the next thing we would do if we inserted one more, right, was just create a new node. We initialize these to null again, fill it with the data, put that in there. We're going to again go to the end, so we follow each of these links. So I would follow the head pointer, and then this one, and then we get to the end, which is here, and then again, what I would say is I set this pointer equal to there, and that pointer equal to there, and then I'm done. So really the insertion is the same after that point. We're always just going to go to the end of the list and then set it to point in both directions. Basically the same as the single list insertion. The only extra step is just setting the previous pointer, because now we have a previous pointer to actually set. Any questions on that one so far? let's create another one here. The lookup is actually going to be exactly the same, so I'm not even going to write that one out. It really is just the same code, so consider, maybe we'll just look at it really quick, that unless I keep a tail pointer and I want to do maybe something efficient and I know this is sorted or maybe something like that, then I can't really do anything extra with the fact that I have a doubly linked list. So the lookup or the get, whichever you decide to do, is just the same. So you have something like that, and then this is null, and this is null. And then we have a head pointer. So if I wanted to get, and so we said like this would be index 0, index 1, index 2. If I wanted to get the object at index 1, then I still need to start at the head and then just work my way backwards. I could maybe be a little bit more efficient if I had a tail pointer and followed from that end. Like for instance, if this was 100 elements long, if I had 100 of these guys pointing in both directions all the way down, and I knew the index I needed to get was something like 87, then I could check if it's greater than half the length of it, then I should go from the tail end and then go backwards instead of forwards. But that's okay. I guess we don't really need that because we're not keeping a tail pointer like a pointer to the end of the list. But that's really one not advantage, but one optimization you could do. It's still not very great because, you know, again, an actual array just goes straight to where it needs to go, and then this one, it just can't do that. It has to follow the links, right? So the lookup for linked lists is pretty terrible, which is why we don't use them a whole lot, but it depends. Some languages do use it some way. Right, so I guess my point here was not the insertion, but the lookup is exactly the same if we just consider it the way that we've been doing it. We just follow the head pointer until we hit that index or thing that we're looking up if we do it that way. So there's no difference. It's the same. So I'll pretty much just copy and paste the code when we get to that. Now the last thing would be deletion. And now we have to worry about two pointers getting reassigned potentially. But we also have a bit of an advantage here. So I'll say this point's here, this point's here, and then these point to wherever. So let's say I want to delete this one again. Now, I guess I do have to worry a little bit because previously my deletion was just, oh, I need to redirect this arrow around this thing first and then delete it. But if I do that now, then these are broken. So this will point to the next here, but this previous is not going to correctly point to the previous. It's still going to point to this information that we deleted. So what I'm going to need to do in this one is also redirect this previous pointer around and then also bring that to point to the new thing. And then after I have both of that done, I can go ahead and delete it. So there's one extra step here, but you'll notice it actually is probably a little bit easier than the previous one. And the reason being is that, right, it was what we always said was we had some sort of pointer to the object that we're deleting. So I guess that would be this red arrow here. This is the object we're deleting. But because we have a pointer to the previous object in the list, we actually have the ability to go back and not have to keep track of the previous the whole time we're going through the list, like we had to last time, where we kept two pointers and then traversed both of them at the same time and then kind of updated them both simultaneously. We can just use one pointer here and then just refer back using the previous. So the idea is when we get to our current, which is the one that we want to delete, we'll set the previous pointer's next. So the previous being this one. So let me maybe color these. So this one we'll just say is yellow. This one is green. I'll do this here in red. So if this is the current pointer, then the previous would be the yellow one. So the previous will take that one's next, which is this part right here, and we'll set it equal to the current's next. Right, so I'll make this one point to there, and then what I'll do is I will take the next one, so that's the next object, and I will make it equal to, I'll make its previous, which is this part here, and I'll make it point back to there. So we'll set it equal to the current's previous, and that's really all we should have to do. And then maybe we just need to consider some special cases again. Right, so I don't need to keep an extra pointer, I just need to do these two things, and then we're done, we're set. Now, let's consider two special cases, and maybe if we have to do something extra, I don't quite remember, but we'll figure it out. So what if the object we're deleting is the head? Well, we are still going to have to do something special there. Because if I delete the head, then I know I need to actually set the next part equal to the head, right? Because if I remove the head, then I need a new head. But let's consider the other part. So if I do the previous next, then I'm going to have an issue there because the previous is null, which means that I can't do anything with it. So if I set the previous next, I'm going to get a seg fault because the previous is null, so it doesn't have a next because it's just not there. Basically, there's no node over here, right, for there to be a next of if I was to remove this one. So I'll need to check if the previous is not null, then I'll do this, and then likewise I'll probably need to do that over here, right? So if I deleted the tail, then if I tried to set the next's previous, then I can't really do that because there's nothing over here for there to be a next of. And then I think that's it. So those are just the two cases we need to actually account for. So we'll just check for those, and that will be the only extra thing we have to do. Right, so let's go ahead and code that. So void insert, void delete at, and it's really going to be almost the same code. We just have the one extra step where we set the previous is pretty much what we said. So let's go here, copy this, and then we'll just paste it. And then we said we don't need a previous node anymore because we keep track of it in the list itself, because it's doubly linked. Okay, so if the current node is null, so this was just the exception that I handled. We don't need a previous node anymore, we deleted it. And then current node is equal to next. So the for loop is the same, right? We're just going to go through until we hit the end of the list. Or sorry, until we either hit the end of the list or hit the object that we need to delete at, and then we need to check some things. Right, so if we're gonna need to change this here. So let's go ahead and do this. Right. So what I think we'll do here is let's just check if the index is 0, then we need to reassign the head. So what I'll need to do is set the head equal to the current head's next. So if we remove the head, we need a new head. Okay, so we'll address that, which I think we talked about last time. And then we also needed to address the other two things. So let's just put an else here, I guess, and then we'll just put it in the body. I think that's easier to read. So if we said if the previous was null, then we couldn't do this part, and if the next was null, we couldn't do this part because then they don't have pointers themselves. So what we'll say is if the previous does not equal null is another way of thinking of it. So if it is null, we can't do anything. If we flip around our thinking, if it's not null, then we can do something. So if it's not null, we will set the previous next equal to the current next. So the previous, actually, I guess we have a pointer here. So the current node, that one's previous, equal to the current node's next, I think is what we said, right? Yep. So that looks good. I think I just need to actually type the right word. So current node's next. And then we also said if the next is not null, then we'll do basically the opposite. We'll say current node, that one's next is going to be equal to the current node's previous. Oh, I didn't even type the whole thing in. I said the previous next and the next previous. Yeah. This might look a little jarring in the code, but hopefully this diagram helps a little bit with understanding that. Right, so that should actually do the deletion here. Cool, and then we delete the actual node that we wanted to delete. Okay, I think that about covers the deletion, and then the other one was the get at or lookup at, which was really just the same thing. Maybe I might just change it to do the index. I know I said I wasn't going to, but I think it's just easier if we do it that way. That's really just the same. And I need to make sure to make these double nodes if I haven't already. Let's just make sure it compiles at bare minimum, and then maybe we'll write the function just to make sure that it is indeed working. So it did compile. That's good. And it runs all the stuff from last time. Very nice. Okay. Let's try to finish writing this then. I don't have a print function, but it is just the same print function, so I'm just going to, again, copy and paste that. I think it's okay. Oh, this is the one I just wrote. Here we go. Right, so we'll just say void that double node. And that should be it. Okay. Let's try to write one really quick. So we'll make a doubly linked list. Oh, I need to actually include the header file. So include, we call it doubly linked list.h. Okay, so now I have a doubly linked list. We'll call this one dlist, I guess. Argument list for class template is missing. Oh, I need to give it a type, right? Maybe we'll put a string here. Okay, so we'll say dlist.insert hello insert world, and then I don't know, we'll put at the end like what's up. So let's try printing that really quick, see if that works, and then we'll delete the one at position 1, see if that works, and then we'll print it again. So what we should get here, right, is that it prints the whole list, all of these things, and then it deletes the word world, which is at position 1, because this would be at 0, 1, and then 2, and then it goes and prints again. What seems to be the issue? Mismatch in formal parameter list. Of what function? Project linked list, file doubly linked list, line 92. Doubly linked list.h 92. Node use of class template requires template argument. I probably didn't finish writing something somewhere. Where does it say? Oh, duh. The double node needs to point to another double node. Ah, there we go. Hopefully that should be okay. I don't need to put the type on that one, do I? I guess I probably do, huh? Oh no, it didn't require it there. Okay, maybe it just infers it. I don't know. Mismatch in formal parameter list. Doubly linked list line 92, which was the constructor? Am I missing a brace somewhere? Mismatch in formal parameter list. It's not call though. I don't know why I would say that. Unless I have a syntax error somewhere. Oh, this is not main. I have so many files now. Like these look right? There's no difference there. Do I have to specify the type? Did I have to do that before? I guess I wrote everything outside of the class. Let's try writing this outside of the class. Maybe it just doesn't like it in there for a template. So let's say template class T. Then I want to write doubly linked list T, doubly linked list, and then my body was just that. Now it seems to be the problem. Oh, there is no parameter list. There we go. No, mismatch in formal parameter list. Line 92, which is nothing. It seems to be thinking this is a call. I'm going to keep this in here then. I think I'm missing a brace somewhere. Mismatch in formal parameter list. But it seems to be talking about the class declaration, which doesn't have a formal parameter list. What have I done wrong? Let's start deleting things. Does it say the same thing if I still do this here? Print is not a member of... Oh yeah, so it's saying I can't do any of those. But it doesn't give me the same error as before. Maybe... Let me include string. Perhaps that's it. No, mismatch in formal parameter list. Let me try a list that's not a string really quick. Int, and then now these need to be ints as well. So 4, 7, and 12. Mismatch in formal parameter list. It's not giving me a very helpful error because it just takes me to the end of the class. So there's clearly... I think I'm missing a parenthesis somewhere. Maybe? Alright, let's try removing functions one at a time. Does it compile without insert? No. Does it compile without delete at? Yes. Okay. So I'm missing something in my delete at. The question is, where did I make a mistake? So delete at index. I didn't do a declaration beforehand of it, right? Void delete at delete current node. If anybody sees a missing paren, let me know, because I think that's what it is. Let me try commenting out the majority of this, and we'll just see if it's okay. Which is being defined. Double node previous uses double node which is being defined. Did I not set head to be? No, I did. Double node T previous uses double node T, which is being defined. Doubly linked list. It says line 9. It seems to take an issue here. I don't think I have to specify the type, but let's put it anyway, see if it's just angry about that. No. Maybe I just have to come back to this at some point, or I might have to work on it later. I don't know why it's not taking it. I mean, it's the same way we coded the last one, right? I didn't put the type on that one, and it was okay with it. What if I do it on 2 node or 2 lines? Is it okay with that? Oh, this is supposed to be a pointer. Yeah, I don't see what the problem is. What happens if I remove this whole class? And that's gone. I'm clearly like missing a colon or something somewhere. It's not really giving me any sort of insight as to where that is. So I guess we'll come back to this. Well, and we won't come back to this. I'll post the fixed code at some point. As long as, does everybody understand the process for this? I guess I should put in one extra thing here. So that was just to account for the fact that we are not using a non-static function. Right. Any questions on this? I think this is more important than the code. I'm pretty sure it's written correctly. I'm just not exactly sure what the problem is with my syntax. I'm thinking I'm maybe missing a bracket or something, and it's just not giving me a very helpful message. Okay, then I guess if you don't have any questions on that, would you rather? So we have 10 minutes left. Would you rather talk about the sorting part using a doubly linked list, which is basically just the same as the part that we pretty much finished last time, or would you rather talk about review for just the last 10 minutes? Because I don't want to start on the next topic. It will definitely take me longer than 10 minutes. Maybe review? Fair, okay. Maybe we can do that. Any other input? No, yeah, we can definitely do review. Do you agree? Okay. Fair enough. Maybe we'll do review then. Any questions then on review? I can pull up the syllabus just so we have an idea of what the topics are. Okay, so any questions in general on anything highlighted there? Exception handling? Yeah, we can do that. I think that's fair, just considering you guys have that assignment this week. So exception handling, what we have is we want to catch some sort of exception in our code, and so the way we do that, right, just to briefly discuss it, is we put whatever code we want to try to execute in a try block. So we use the keyword try, and then we put whatever code there, and then we put a series of catches. So maybe while I'm writing this, I should actually reopen the exception handling that we had from before. I think that was this one. Right, so we put some sort of exception here. Exception E. And then we could have any number of catches here as well. Now, I'm pretty much just going to be writing code for this one, so I will just open this up. So what we had was this fraction class originally when we were doing the exception handling. And I think the exception that we were concerned with was trying to do this here. Maybe I can rewrite it too, just to be a little bit nicer. So the idea was, on this one, if I wanted to do division using a fraction, then one thing I shouldn't be allowed to do is do division by 0, because that's not really allowed as far as fractions go and just math. So what we did here was I created a class called fraction divide by 0, and it was an exception type. Now you can use the exception types that are built into C++ as well. So there's the actual type called exception, and then there's some other ones like bad allocation or logic error or whatever that I posted a link to on Canvas. And the idea was that we can try to run some code, and if we happen to run into an error partway through, we can throw that error and catch it. So what I did here is, in my get int value, which did the division of numerator divided by denominator, was what I was supposed to do, is if the denominator was equal to 0, I know I'm going to end up having an exception. So what I would do is I ended up throwing it. So we had that keyword throw, which is the one that actually raises the exception, and then you can say specifically what exception it is that you want to throw. So here I wanted to throw this fraction division by 0. Now you can also throw other exceptions. So if I did something like if denominator is less than 0, then maybe I don't want a negative number for some reason, then I can throw a normal exception or something like that. Let me construct a new one. And what this will do is it will throw specifically an exception. So what the compiler, or I guess rather the runtime environment does, is it will, whenever you throw an exception, it will check if it's in a try block, it'll find the most recent try block that you're in. So I could actually have multiple try blocks. I could, in fact, just envelop all of this in a try block and then put catch exception E, and that would be okay. That's allowed too, and then code after that. But it'll find the most recent try block, the one that it's inside of currently, and it will use that one to throw the exception. So when I throw, let's just say this exception here, it will go and say, okay, I'm throwing an exception. And then it will look through here and try to find the best match. So it basically does like an if, else, if kind of check, where it checks, is this that same type of exception? If so, execute that code that's at the catch. If not, go and check the next one. So here, if I wanted to, I could throw and say catch exception. Now this wouldn't be very good here for me to do this, but I could say catch exception E. Now the problem with this code is that fraction division by 0 is also an exception, and this is just the generic like parent class for everything. This is the base class exception that everything inherits from. So this one also inherit from there. So what would happen is if I threw either of these, it should actually just go down here and execute this one. So I probably want something a little more specific, or perhaps just to throw it down here. I'm copying and pasting the wrong code. So catch exception E. Right, so what it did was it would go through whenever you throw one and check, does it match? So let's just say it through this one. It would say, is fraction division by 0, is exception a type of fraction division by 0? And it's not. So this is more specific than that one. An exception is not a fraction division by 0 exception. Those are not the same thing. So it would go down and check the next one and say exception, yep, that's definitely it. And then it would execute whatever code's here once it has that exception happen. So it really will just, whenever an exception gets thrown in a try block, it will go through each of the catch statements, check, is it that type of exception? If so, execute the code in that catch block, and then, just keep going. Now, it won't go back to the try block, so if you happen to get this exception thrown, it will not execute the rest of the code in the try block. It will just go to the catch and then skip over to the end down here, past everything. The other two things to note about that were that there's a few different keywords that you can throw here. So you can put catch ... in C++, and that will just catch everything else. So if you happen to throw an exception that's not fraction division by 0 and not exception, it'll just go down here and do this if it doesn't happen to match anything. So it's kind of like your default case in a switch statement. If it falls through everything, it ends up there. I think you're also allowed to use the word in place of that finally. Finally is undefined identifier. Okay, maybe not. I don't know why. Normally that's used for the same sort of thing. I don't know why it's saying it's an identifier and not a keyword, but this is, I guess, an option. I usually just write this at the end of mine, or alternatively, I don't think C++ allows this, but I think you're allowed to just write the word catch in something like Java and C++, and that will just catch everything else too. But I guess C++, the syntax is this with the ... So really it's just a way to, if you know you're about to encounter an error, you can actually encounter it a little bit early. One other thing, let me just pull open the other example really quick, and then we'll just end on that note. Where, yeah, right, well that, I just closed it. It was the linked list one. Where it could be a little bit more helpful is if you know you're going to call a few functions that all actually have some sort of exception. So what you'll notice here is that I had an exception that gets thrown in the delete function itself. So you'll see here in the delete at, if I go to the definition that I wrote, I have an out of bounds exception, which was a custom class that I wrote, and it gets thrown if we are about to do an index that would go past the end of the linked list. and then I throw an out of bounds exception. So what I can do is throw that in the context of the function, not handle the exception at all, so put no try block in the function itself, and let whoever is calling this function handle that exception if they think it's worth their time. So you'll notice here I throw an exception in delete at if we're about to go out of bounds, and then here I handle that exception when I call the function itself. So if it gets thrown, it will check for the most recent scope, so it will kind of work its way up until it finds the place where the try block is. So if there is a try block, if not, it will crash and just give you a message. Well, I guess not crash, but it'll stop the execution of the program and give you a pause to tell you about the exception. So this is just a way, right, to not have that happen if we do that try block, is to make sure that the execution of the program keeps going and that we handle it in some way if we happen to get an exception. Whether that be an exception class that you've written yourself, or whether that be something like a division by zero error, or a standard invalid argument error, which a lot of you have gotten when you use s to I and then give it something that's not an integer, it maybe throws you that. You can do like try block around that and then say catch do nothing, and then just ignore junk or errors without having your program entirely crash on you, is you can just put the try block. And you can do that around function calls, I think was the point I was trying to make here. So delete at is the one that throws the out of bounds exception, and if it gets thrown, I handle that back here in main where I'm going to be using that function. So really all you need are these try and catch parts, and then you can, up to however you decide to do it, catch errors that you think might happen without having the program crash, of course. If that all makes sense. I know that was an entire lecture condensed into like 5 minutes, but hopefully that was okay. Right, any other quick questions before we go? Okay, then on that note, I will see you all next Monday. We have no class next Wednesday, so Monday will be the review, and then we have the exam the week after that. If you have questions, please make sure to think of them before we come to class on Monday. That way you can ask them and we can just go through it for that whole class period. Alright, well, I guess on that note, then I will see you guys on Monday.